The last topic of today is the inverse matrices. So inverses means the matrix that satisfies this condition. So when we learned in the number algebra, as I said, we can consider this I, the identity matrix, as number one in the number algebra, right? So what we have learned the inverses before is like, for example, you want to find the inverse of 2. That means that you will need to find a number such that 2 multiplied by this number equals to 1, right? So this number is called the inverse of 2. So we know that this is 1/2, right? So this is the concept of inverse in the number algebra. But in matrix algebra, it's something similar. So we need to find, so given matrix A, we need to find another matrix such that when this matrix A multiplied by this matrix, the result is an identity matrix. So it's kind of similar to the number algebra, but we need to find this matrix in the question mark, right? It's not that easy to take the inverse, like a 2 and a 1/2 or something like this. It's very complicated to find the inverse of the matrix A. Right. So this matrix, we call this A inverse. There's a -1 sign here. So A inverse is the inverse matrix of the matrix A. Right. So A times this inverse matrix equals to this inverse matrix times A equals to I. So you can think of that like 2 times 1/2 equals to 1/2 times 2 equals to 1, as in the number algebra. But here, everything is matrix form, so it's not that easy, right? It's not that easy to find inverse matrix. And here's a condition for the matrix A, is that A has to be a square matrix. It has to be a square matrix, right? N by N square matrix. Otherwise, A has no inverses, right? We have to remember that if A is like 2 by 3, we haven't talked about how to actually calculate the inverse or how to actually find the inverse of the matrix. We learned that in chapter 5. But here, just remember that A has to be a square matrix, because when we are finding the inverse matrix, it has to be a square matrix to do the calculation, step-by-step calculation. Otherwise, if it's a like rectangular matrix, then there's no way that we can find a inverse matrix like that. So it has to be a square matrix. And A inverse with this notation, -1, is the inverse of A. It's called the inverse of A. Right? And yeah, some of the notes. Not every square matrix has an inverse. Right? Not every square matrix, even though this is a square matrix, but not everyone has an inverse. Right? It has to meet a particular criteria. And this is our major topic in chapter 5. Right here, just some like concepts here. Right. So if the inverse matrix exists, then A is called non-singular matrix. Otherwise, if there's no inverse matrix, then A is called a singular matrix. Okay, just some concept. And A and A inverse are inverses of each other. Well, of course, because given A inverse, its inverse matrix should be A itself, right? Because A inverse times A equals to I. And given A, this matrix, its inverse should be A inverse, right? So A is the inverse matrix of A inverse, and A inverse is the inverse of the matrix A, right? So the inverses of each other, because we'll multiply this no matter the order, the result should be the identity matrix. Okay, and if the matrix A is n by n, then its inverse is also n by n, right? Because when you multiply these two things together, if A is n by n, as we said, it has to be a square matrix, right? So let's assume it's a dimension n by n. So you have to make sure that the column vector of the A should be the same as the row vector of A inverse, right? So these two numbers are the same. So this is n, this is n, but suppose we don't know the column dimension of the A inverse, but we know that the result is a identity matrix, and all the identity matrices are square matrix, right? So all the identity matrix should be square matrix. And we also know that the resulting for the I matrix, identity matrix, the dimension should be m times something, right? Because the dimension of the resulting matrix should be the dimension, the row dimension of the first matrix and the column dimension of the second matrix, right? So it has to be n by something, and it is a square matrix, so it has to be n by n. So this is n by n, so the A inverse should also be n by n, right? The idea is just A is a square matrix, I is also square matrix, both of them has to be n by n, right? So we know that A inverse has also be n by n matrix. And if an inverse exists, then it is unique, right? So you cannot find two matrices that has the same inverses. So we can, if you're interested, we can prove this if B and C are both inverses of A, right? So then A times B equals to B times A equals to I, right? By the definition, because B is like A inverse, right? It's inverse of A. So C is also equal to A inverse because C is also an inverse of A. But suppose that these two inverses are different. Right? Suppose these two B and C are different. And so because A times B equals to the identity matrix, so if we pre-multiply C, matrix C, in before A, B, and I, then the result should also be the same. Right, because AB and I are the same thing. So C times AB should be equal to C times I. Right. So we know that C times A is identity matrix by the definition here. So this becomes I times B. Right. C times A times B, because this is identity matrix. So this thing becomes I times B, as I show here. And the right-hand side is also C times I. And we know that the identity matrix times anything is the matrix itself, right? It doesn't change the matrix here. And so this downgrades to B, so this is equal to C. So this means that B equals to C, right? So the two inverse matrices are the same thing. So here we end the proof. Okay, so this proof just means that suppose we have two inverses, B and C, and then by definition and by some simple like a derivation, we can find that B and C are equal to each other. So that means that the matrix A has only one inverse matrix. Okay, and the last one, A times A inverse equals to I. and it's equal to say that A inverse times A equals to 1, right? When you see this, then you can know this. From this, we can know this. So from the first statement, we can know the second statement, and from the second statement, we can know the first statement, right? So they're the same thing. So this sign means if and only if, or also means that if the first statement holds, and so the second statement must also hold. And if the second statement holds, then the first statement should also hold, right? So, or we can say that A times A inverse equals to A inverse times A equals to I. Right, so the order doesn't matter. And here are some of the properties. So if A and B are non-singular matrices, so non-singular matrices, again, it means that there is an inverse matrix, right? The inverse matrix exists. So if A and B have inverse matrices, and A and B are of dimension n by n, then we have three properties. First is that the inverse of A inverse is the matrix A itself. So it's kind of like you'll find, for example, you'll find the inverse of 2, right? So it's 1/2. And 1/2, the inverse of 1/2 is just 2 itself, right? The inverse of the matrix is the matrix itself. Okay, so it's easy to understand. So the second one, the inverse of the product of A and B should be equal to B inverse times A inverse. So this is kind of like when we're talking about the transpose, right? A and B transpose equals to B transpose times A transpose. So we have to change the order here, right? It's not A prime times B prime, right? It's not like this. You have to change the order. So we can prove the second one here. So suppose C equals to the left-hand side, AB inverse. And then we know that C times AB should equal to the identity matrix. It's because C is AB inverse. And then you times another inverse. Another AB, right? So this should be just the identity matrix here. And so this thing times B inverse A inverse should just equal to I, right? Because we know that CAB equals to I. So this is just I times the same thing. And we know that the identity matrix, the product of identity matrix and any other matrix should be the other matrix itself. So I times this matrix should just be the matrix itself, right? B inverse and A inverse. Okay. And so we can rearrange this like this. So we don't change the order, right? So this is CAB, B inverse, A inverse, and we multiply all of them together. So if we don't change their order, we can combine any of them and calculate first, and we don't, it will not affect the result, right? This is because A times B times C, as we learned earlier, equals to A times B and C. As long as the order are the same, we can combine any of the two matrices and calculate them first, and then calculate the rest of them. Right. So here we can combine B and B inverse first, and calculate this first. Right. So the right hand side is also B inverse A inverse. And the B times B inverse is just identity matrix. From here to here, just the identity matrix. Right? So this becomes C times A times identity matrix times A inverse. So the right hand side is still B inverse A inverse. And we can get rid of this identity matrix, right? Because identity matrix times any kind of matrix is a matrix itself. So we can get rid of this I and then combine A and A inverse, right? So this becomes CA I A inverse. Get rid of this I, so this becomes CA A inverse. And then we combine the last two matrices. And because A times A inverse is another identity matrix, right? I. And so this becomes C itself. So we can know that C is just B inverse A inverse. So C is AB and the inverse. Then after some derivation, we find that C is B inverse A inverse. So we can prove that the product, the inverse of A times B just equal to B inverse times A inverse. Okay, the last one, A prime and then inverse should equal to A inverse and then prime, right? Or the inverse of A transpose should equal to the transpose of A inverse, right? You can interchange the two signs here. Okay, let's prove this. We can let a matrix D equals to the left-hand side, A prime and the inverse. So D times A prime equals to I, right? So this because D is equal to A prime inverse, and this thing times A prime, right? So this should be just the identity matrix, right? Because this is just a matrix, the same matrix. The inverse of the matrix times the matrix itself, it should be the identity matrix. And because we know that A times A inverse and then prime is just the identity matrix, right? Because A times A inverse is just I, so this becomes I prime, and I prime is just I, right? When you take the transpose of this identity matrix, as I said, it's like to flip the matrix along the diagonal here, and all the diagonal elements are just one, right? So, and all the other elements are zero. So when you take the transpose, like take the flip of the matrix, it doesn't change anything. It's still the identity matrix itself, the same identity matrix. Right, so I prime is just I. So dA prime is equal to I from here. So I is equal to A times A inverse and then prime, right? So this becomes A inverse prime times A prime, right? So this last equation comes from this formula. A times B and the inverse, A times B and the transpose equals to B transpose times A transpose. Right, so here the B matrix is just A inverse. Right, so A times A inverse is equal to A inverse and then prime times A prime. Right, because okay, so this is the equation here. So we know that dA prime just equals to this thing. So we can post multiply A inverse, A prime inverse on both sides of the equation, right? So dA, this thing, times this matrix should just equal to this matrix times this thing, but because dA prime is equal to this thing. So when you multiply another matrix behind all of them, behind both of them, the results should be the same. So dA prime times A prime inverse is just D times I, right? Because this is just I, and it's just the D. And also A inverse prime, A prime inverse. If you combine the last two, it should be times I, right? Times I. So this is just A inverse and then prime. So we can know that D is just equal to A inverse and then prime. And because D is this, and from some derivation, we know that D equals to this. So that means that A prime inverse should be equal to A inverse and then prime, right? So here is our proof. Okay. So here in chapter 4, we just talk about some of the concepts of inverses. And in chapter 5, we'll continue to learn a lot of things about finding the inverse matrix. Okay.